New type of function, new to us anyway, exponential functions. An example of an exponential function will be 2 raised to the x power. You can compare this with a polynomial function that we would have seen, well, in section 3.1, quadratic functions, x to the second power, kind of a role reversal. Rather than having a variable base and a constant exponent, an exponential function is characterized by the presence of a constant base, the number 2, in this case is the constant base, and it's a variable exponent. It exhibits different properties than polynomials do, but there are lots of physical quantities that relationships between them can be best described using exponential functions. So start off with the definition. Exponential function f with base a is denoted by f of x equals a to the x power. We'd like x to be any real number. We'd really like the domain of our exponential functions to be the set of all real numbers, the graphs to go all the way to the left, all the way to the right, and in fact, not even any discontinuities, no gaps or holes in the graphs. In order to make that happen, what we need is to restrict the value of the base only to positive numbers, and one additional restriction, not so much for the domain, but just to make exponential functions behave like they behave, we'd like a not to equal 1. We want a to be greater than 0 because if we were to define, say, a function f of x equals negative 64 raised to the x power, for a lot of values of x that would be okay. You can raise this to any whole number power. Just take 64 to the first negative 64 to the first power, negative 64 to the second power, negative 64 to the third power. It just depends on how many negative 64s you want to write down and multiply them all together. You could evaluate this for any whole number. However, if x is a fraction, and there are other possibilities for this, but in particular if x is a fraction, you could run into difficulties. F of 1/3 would not be a problem. Somebody makes sense of the expression negative 64 raised to the 1/3 power. What does that mean? We don't talk about fractional exponents that much in this course, but in the last algebra course you took, probably, they hit them hot and heavy. What does this mean? It is the cube root. We raise to a fractional exponent. The number in the denominator tells us what root to extract. Number in the numerator, if there's something different from 1, tells us the power to which it must be raised. So the cube root of negative 64 is a real number. Yes, what real number can you multiply by itself and by itself again and get negative 64? Negative 4 will do it. So this would not be a problem, but this would. If raised to the 1/3 power means take the cube root. Raised to the 1/2 power ought to mean take the square root. And what is the square root of negative 64? It is an imaginary number. It is 8i, and we would very much like our exponential functions to be real valued. Pick a real number, any real number, put it in, get a real number as the answer. So, to make that, to ensure that that happens, the base, the 2 in this case, must be a positive number. Now, we don't want it to be 1, just because that would be boring. F of x equals 1 to the x power. 1 to the first power is 1. 1 to the second power is 1. 1 to the third power is 1. 1 to the 1/2 power is 1. 1 to the 1/3 power is 1. More properly, this function belongs to the set of polynomials. It's a constant polynomial. It's f of x equals 1. So we don't regard it as an official exponential function. So if the base is positive, if the base is different from 1, then a to the x power is an exponential function. And what we'll see in a little bit is we'll be able to further subclassify these exponential functions. There'll be some exponential functions where the base, we'll just think about what are the numbers that are positive and different from 1. Well, there's 0 right there. We're not including 0, but get a little bit greater than 0, and it's okay. There's a 1 right there. Don't include 1. And that basically divides the real number line into 2 intervals. The interval where the numbers are between 0 and 1, and the interval where the numbers are greater than 1. So for the next example, I've chosen an example of each. The graphs look different if the base is greater than 1 than they do if the base is between 0 and 1. So I've chosen the number 2 from in here, and I've chosen the number 1/2 from in here. Let's look at these graphs and see what they have in common. I guess maybe not so much what they have, well, a little bit what they have in common. The relationship between them and the important difference between the graphs. So example 1, compare, contrast, if necessary, these 2 graphs. Oh, and to graph these, it's very helpful. I mean, it's good to use it's helpful to use a calculator. It's also helpful to be able to take the number 2 and raise it to various different integer powers. So just so we're good with this, what is 2 to the first power? It's 2. What's 2 to the second power? 2 times 2. 2 to the third power? 2 times 2 is 8. How about 2 to the 0 power? What's that?
1.
It is 1. 2 to the negative 1? It is 1/2. 2 to the negative 2, officially, that's 1/2 squared. That's 1/4. And in a similar fashion, 2 to the negative third power is 1/8. Now, armed with these facts, we should be able to graph both of these. So f of x equals 2 to the x power. Just going to choose some nice numbers in its domain. Basically, I'm going to choose all the exponents that I had there. From -3 to +3, the x values are the exponents for exponential functions. So I'm going to evaluate the function at 0, 1, 2, 3, -1, -2, -3. And we could go as high as 8 for this. So that's 8, and that's 4, and that's 6, and that's 2, and that's 1, 3, 5, 7. Let's see what we get. 2 to the, where to start? Maybe in the middle. 2 to the 0 power is 1. So we'll have the point 0, 1 on the graph. Now, the base here is 2, but suppose it were 3. What's 3 to the 0 power? It's 1. What's 4 to the 0 power? That's 1. Even 1/2 to the 0 power, when we see it, that's also going to be 1. So what we'll notice at the point 0, 1, before we do any shifting or stretching or reflecting, point 0, 1 is going to be the y-intercept for these basic exponential functions. 2 to the first power is 2. So the x-coordinate is 1, the y-coordinate is 2. So we plot the point 1, 2. 2 to the second power is 4. So 2, 4. And to the third power is 8. 2, 8. Notice each time we take one step to the right. Since the base is 2, we multiply the y-coordinate of the point on the graph by 2. We go 1, and then 2, and then 4, and then 8. If we're taking steps to the left, 2 to the negative 1 is 1/2. 2 to the negative 2 is 1/4. 2 to the negative 3 is 1/8. It would appear that we are getting closer and closer and closer. Maybe as close as we could possibly want to be to the x-axis. When do we actually get to the x-axis? How far to the left do we have to go before we get to the x-axis? X-intercept. 1/8, 1/16, 1/32, 1/64. When do we get there? Never. Never. It's a horizontal asymptote. Well, we saw some graphs actually intersect their horizontal asymptotes, but these exponential functions do not do that. They will approach them, they will not intersect them. So it gets as close to the x-axis as you could possibly want it to be. But, oh, come on. Nice curvature there, but it does not cross the x-axis. All right, make the dots bigger, like those dots to be on the graph. There we go. For the graph of the other one, we can do this one point at a time, but we'll look at some transformations in the next example. And let's go ahead and start with a, excuse me, go ahead and start with the transformation here. 1/2 to the x, so I want to rewrite that. 2 to the negative 1 to the x. Over here, we observe that 2 to the negative 1 equals 1/2. So 1/2 ought to equal 2 to the negative 1. Power rule for exponents. If we have a number and that's raised to a power and that's in parentheses and that's raised to a power, what do we do with the powers? Multiply. Negative 1 times x. So this is 2 to the negative x. Now, back to section 2.7. All those transformations, shifting up, down, right, and left, stretching, shrinking, reflecting. If we substitute, if we have the graph, we have an equation of a function, and we substitute negative x for x, everywhere we see an x, what does that do to the graph? It is a y-axis reflection, yes. It changes the signs of all the x coordinates. Positive x's become negative, negative x's become positive. So it results in a y-axis reflection. And if I can make this happen, we will see it. 0, 1 stays put. 0, 1. Because points on the y-axis do not move when you reflect about the y-axis. The point 1, 2 goes to the point negative 1, 2. The point 2, 4 goes to the point negative 2, 4. The point 3, 8 goes to the point negative 3, 8. And let's see, negative 1, 1/2 certainly ought to go to the point 1, 1/2. I would like to believe that if we take 1/2 and raise it to the first power, we get 1/2. And let's see, negative 2, 1/4 goes to positive 2, 1/4. And negative 3, 1/8 goes to positive 3, 1/8. Whereas the graph of fx equals 2 to the x is rising, so it's an increasing function. The graph of g of x equals 1/2 to the x is falling. So it is a decreasing function on its entire domain. It's a decreasing function. The base 2 is greater than 1. This is kind of an example of a base that's greater than 1. Just think what happens. If you take a number that's greater than 1, like 2, and start multiplying by itself again and again and again, the more factors of 2 that you have, the greater the number is. 2 times 2 times 2 times 2. Each time you multiply by 2, the number gets bigger, twice as big as it was before. So it's increasing. On the other hand, suppose you start multiplying by 1/2. You start somewhere and start multiplying by 1/2, and then cut it in half again, and then cut it in half again, then cut it in half again. More times you cut something in half, the smaller it gets. So for an exponential function where the base is between 0 and 1, we could have done it with 1/3 or 1/4 or 2/3. You multiply something by something between 0 and 1, and the result is smaller than what you started with. So it gets smaller and smaller and smaller. It's decreasing. So what we'll see, I guess we've already seen it, is that exponential functions with base greater than 1 are increasing on their entire domains. Exponential functions with base greater, let me say it again, I think I said it wrong. Exponential functions with base greater than 1, like 2, are increasing on their entire domains. Exponential functions with base between 0 and 1 are decreasing on their entire domains, like 1/2 to the x. Summary here, let's see if I missed anything. I kind of did, yes. I mentioned domain. I didn't specifically address the idea of range, so I should do that. Both these graphs go all the way to the left and all the way to the right. However, they don't go both all the way down and all the way up. So whereas the domain of both of these is the set of all real numbers, the range of both of these, how low do they go? Well, they almost go to 0. As close to 0 as you could possibly want them to go. They just don't quite get there. So we could say 0 is the greatest lower bound. But they do go all the way up, both of them. One on the left, if you go far enough to the right, it'll go as high as you want it to go. The one on the right, if you go far enough to the left, it'll go as high as you want it to go. So 0 to positive infinity for the range of each of these. Each one has a horizontal asymptote. Did mention that. It is the x-axis, aka y equals 0. Be sure to indicate the horizontal asymptote in the form of an equation. Don't just say 0. Y equals 0 is what you need there. Example 2. Again, section 2.7. Transformations. Want to begin with the graph. I suppose if we'd like it to be a little cleaner and a little neater, I could capture as much of this as I can. Shrink it down. We'll take this graph, put it up here in the corner, and refer to it as we transform that graph to obtain these other graphs. For each one, want to sketch the graph, want to indicate the domain and range, and horizontal asymptote. These exponential functions do not have vertical asymptotes. They just don't. They have all real numbers in their domain. There's no number where, as x gets close to that number, it just blows up and becomes unbounded in an open interval containing that number. Doesn't happen. So horizontal asymptotes are what we're looking for these exponential functions. F of x equals. Now, we talked at length about why we don't want the base to be negative. We do not want that because we want to have real numbers as the answer. So when we say a negative sign and then 2 to the x power, we're not raising negative 2 to the x power. We're raising positive 2 to the x power and then doing what? Making it negative, multiplying by negative 1. And it actually does make it negative at that point because 2 to the x is always positive. If we put the negative sign in front, then it'll make it negative. So I want to take the graph that we have over there and do to it what multiplying the right-hand side by negative 1 does to a function. What does it do to the graph if we multiply the right-hand side by negative 1? It is an x-axis reflection, yes. So it'll multiply all the y coordinates by negative 1. So 0, 1 goes to 0, negative 1. 1, 2 goes to 1, negative 2. Negative 1, 1 half goes to negative 1, negative 1 half. Everything else goes along for the ride. Let's see, 1, negative 2. And the graph looks like that after the x-axis reflection. Unless we seriously mess with the exponent of any of these exponential functions, we're not going to delete any numbers from their domains. Let me give an example of what I mean by seriously messing with the exponent. If we did that, that would restrict the domain. The domain could not include any negative numbers in that case because of the square root. Not so much with the exponential function, but because of the square root. If we did something like that, I would consider that seriously messing with the exponent. X would not be allowed to be 3. X would not be allowed to be negative 2. But if all we do is maybe substitute x plus 4 for x up in that exponent, that's not going to cause any restrictions on the domain. And the others, I'm not even messing with the exponent at all. So unless we seriously mess with the exponent, the domain of each of these exponential functions is going to be the set of all real numbers. And if you think of the 10 transformations, shifting up, down, right, left, reflecting, shifting, and stretching and compressing, none of those involves doing anything to the x other than maybe substituting negative x for x, substituting x minus a number for x, or x plus a number for x, or a number times x for x, or the number x divided by a number for x. So count on the domain being all real numbers. The range can change, though. Instead of being everything greater than 0, what do we have here? Everything less than 0. Negative infinity to 0. The x-axis is still the horizontal asymptote. It approaches the x-axis from below in this case rather than from above. G of x equals 2 to the x plus 3. What's the transformation that takes place from the original to this one? Start with y equals 2 to the x, shift it 3 units, up, down, right, or left. 3 units up. If we have a function that has a horizontal asymptote, comes ready-made with a horizontal asymptote, and we do a vertical shift, that horizontal asymptote will shift vertically that many units. So it goes from y equals 0 to y equals 3. That will help as we try to sketch this graph. And then the y coordinates of these points each also increase by 3. So 0, 1 goes to 0, 4. And 1, 2 goes to 1, 5. And negative 1, 1/2 goes to negative 1, 3.5. And the graph looks like this. With the horizontal asymptote, we can state the domain is all real numbers. The range, once again, changed, though. How low does this graph go? Well, almost as low as 3. Take the set of all positive real numbers and add 3 to every one, and you get the set of all real numbers that are greater than 3. So 3 to positive infinity. Already named the horizontal asymptote, but I'll name it again. Y equals 3. Because that's in the way. One more, just a real basic transformation. H of x equals 2 to the x plus 4. If we have a function and we substitute x plus 4 for x, wherever we see an x, it will shift the graph 4 units up, down, right, or left. Which way? To the left, yes. X always lies. It's the opposite of what we would think. So 4 units to the left. X can get by with being 4 units less in this case, because we're going to add 4 before we evaluate the function. So 0, 1 goes to negative 4, 1. And 1, 2 goes to negative 3, 2. And let's get one more. 2, 4 goes to negative 2, 4. And to the left there, negative 1, 1/2 goes to negative 5, 1/2. I mean, you can plot numbers. You can substitute different x values, different integers, and just evaluate the function. But I think it's helpful to do this with a transformation. Now, I have to be careful. If I'm not careful, it would appear that there's perhaps a vertical asymptote at the y-axis, but the y-axis is not a vertical asymptote. In fact, there is a y-intercept, and it just keeps on keeping on the other side of the y-axis. What is the y-intercept for this function? Or I could ask, what is h of 0? What's h of 0? I don't know if I can fit it on my screen. I have to scoot it a little bit. Now maybe I can fit it on there, although I'm still kind of worried. What's h of 0? 0 plus 4 is 4. 2 to the 4th power, 2 times. It is 16. Can I go as high as 16? That's 4. And that's 8. 16 is, I guess, right there. Okay. It keeps on going on the other side of the 16. Not a vertical asymptote. The domain, all real numbers. I like this one. It's a shift 4 units to the left. So we started with a set of all real numbers, and then we subtracted 4 from each one. What do you get if you start with a set of all real numbers and you subtract 4 from each one? Weird question with a beautiful answer.
Which number minus 4?
Well, yeah, the set of all real numbers that can be obtained from a real number by subtracting 4. And that would be the set of all real numbers. Strange question, weird answer, but it works out that way. So it's a set of all real numbers. So the range, it's changing each time, but it goes back to the original. If you think of the original, the range was all positive real numbers. Just shifting 4 units to the left doesn't affect any y values, just changes the x values that they're associated with. So that's still all positive real numbers. And the horizontal asymptote, if you take the x-axis and just shift it sideways, the horizontal asymptote is still the x-axis. So y equals 0. Example 5. Suppose someone hands us some points on a graph, and we can identify that this graph seems to be that of an exponential function. How do we know it's an exponential function? I don't see the word exponential in there anywhere. But if we look at the y-coordinates, 1, well, I would almost rather have the x-coordinates presented in some kind of order there. Let me write these kind of in a tabular form. X and f of x. If we go with the least one there, -2, and then -1, and then 0, and then 1, and then 2. We just look at what's going on with the y-coordinates. It's 16. And what's happening with -4? 4. And with 0, there's a 1. And with 1, there's a 1/4. And with 2, there's a 1/16. Can you answer this question? Is there something that's happening consistently from point to point to the y-coordinates every time we increase the x-coordinate by 1? We're going, I'm thinking about starting at 16, and then 4, and then 1, and then 1/4, and then 1/16. What's the opposite of quadrupling something? I guess dividing it by 4. That's what we're doing. Is that what it looks like? Are we dividing the y-coordinate by 4 each time we step 1 unit to the right? It's a little tricky though, so I would start with something like f of x equals 1/4 to the x, but I don't think is that quite what it is? Maybe it is. A little disappointed maybe if that's really what it is, because I was thinking we might have to do a horizontal shift to get to this, but 1/4 to the power of -2 I think actually is 16. And 1/4 to the -1 actually is 4. 1/4 to 0 certainly is equal to 1. So I believe this is all we have to do with this particular one. So let me do this. Let's call it example 5.5. I'm going to change the x-coordinates and make them look like this. 3, 4, 5, 6, 7. So what's happening here is a horizontal shift, but I think there's more than one way to do this. I don't think we have to substitute x plus or minus something for x. I think we can go a different way with it. Suppose we write f of x equals a times 1/4 to the power of just plain old x. I think we can make this happen. Because this still has the property that every time we take one step to the right, we're dividing the x-coordinate by 4, or we're multiplying the y-coordinate by 1/4. Each time we take one step to the right. The echo in my head sounded like I said to the left. Each time we take one step to the right, we're multiplying the y-coordinate by 1/4. How could we find the value of a well, what if we did this? F of, and I think we could pick any number from 3 to 7. So someone pick a number from 3 to 7. 4. F of 4 equals A times 1/4 to the 4th power, and coincidentally enough, that equals 4. I think if we find a value of A that works for that particular point, it'll work for all of them. Hope so anyway. We'll check it against the other ones and see. So what value of A works here? This is going to be A times 1 over 256. Is that what 16 times 16 is? 256? What if we multiply by 4 again? I'm thinking A is 4 times 256, which is 1,024. So would you be willing to believe, oh, how did I miss that A? Would you be willing to believe that f of x equals 1,024 times 1/4 to the x power is going to work for all 5 of these points? Someone pick another number from 3 to 7 other than 4. 6? And cross your fingers. F of 6. That's 1,024 times 1/4 to the 6th power. I'm hoping to get 1/4 as the final answer here. This is 1,024 times 1 over 4 to the 6th power. All right, calculator. Is 4,096. Really, is that all it is? I guess so. 4,096 is 1,024 over 4,096 equal to 1/4. I think it is. All right. Check it. Check it for the 3. Check it for the 5. Check it for the 7. Because it has the y coordinates have the property that we're multiplying the y coordinate by 1/4 every time we add 1 to the x coordinate. A function of the form a times 1/4 to the x is going to work, and it's just a matter of finding what's the right value of a. And when we find the right value of a, it's going to work for all 5 of those points. So this is the function that works. Now, in your leisure time, this weekend sometime, you might consider another way. Just pick a equals 1 and see how you can replace x with x minus a number or x plus a number to make that shift happen. But I think that's a little bit more complicated. You have to think about the graph a little bit more in order to do it. All right, so example 6, we should be able to knock this out. Do the y coordinates have this exponential type property where we're multiplying by the same number again and again and again and again? If so, what is that number? Multiplying by 4 in this case. So I'm thinking f of x equals a times the base is going to be 4. So 4 raised to the x power. And we just need to find the right value of a. So someone pick a number from -1 to 2. We go with 1. So f of 1 equals a times 4 to the 1st power, which equals 32, according to the way this is defined. F of 1 equals 32. So that means a times 4 equals 32. So I'm thinking a is 32 divided by 4, which is 8. So the function we want, f of x equals 8 times 4 to the x. Let's check it. Somebody pick a different number from -1 to 2.
2.
How about 2? So check. F of 2 equals 8 times 4 to the second power. 8 times 16, is that about 128? I think that's about 128. So it checks out nicely for this exponential function. Whoa. Simple interest versus compound interest. All right, let's look at the example that we have here, example 7. No, I just don't want to. I'm going to tweak this example. Find the interest earned in the final balance on $1,000 deposited at bank for 5 years at 6%. I just can't think of a scenario where the interest wouldn't be compounded at least annually, and that's kind of the follow-up to this. Sometimes more often than that. So let's tweak this a little bit. I'm going to say, suppose that the interest is compounded, let's say quarterly. Compounded quarterly. So 4 times a year, interest is calculated and paid to the account, and the balance of the account is increased so that the interest that has been paid to the account begins to earn interest on its own. Okay, so it's we're compounding the interest quarterly, every 4 months. So what I'd like to do is consider how we would determine the balance after 5 years only using the simple interest formula, because ultimately interest is calculated unless it's continuously compounded interest, which we'll look at in a little bit. But ultimately interest is calculated using the simple interest formula. The compound interest formula is based on that. So let's just see how we would do it. So balance after 1 quarter. Let's see if we can figure this out. So using the simple interest formula, interest equals principal times rate times time. We're going to take that $1,000 and multiply by the annual interest rate, 0.06, and multiply by the time. 1 quarter is what fraction of a year? I'm thinking about 1 quarter. So 1/4. So it's principal times rate times time, converting that rate to a decimal, of course. And so how much money is that $1,000 going to earn? How much interest is it going to earn in 1 quarter? Well, I'll tell you what. Let me just hold on to that $1,000. There is a particular significance to the 0.06 times 1/4. So let me crunch that out first. 0.06 times 1 divided by 4 is 0.015. 0.015. This is it goes by a couple of names. It's the periodic interest rate. It's basically 1.5% per quarter is what you would think of this as the periodic interest rate. You could also call it the quarterly interest rate. Basically, the balance in the account is increased by 1.5% every quarter. So to see how much money that yields, tell me it's more than $1.50. Is $15? $15. So $15 is how much interest that $1,000 earns in 1 quarter. So the new balance, we take the original principal plus the interest, and that's going to be whatever 1,000 plus 15 is. That's $1,015. $15. So that amount is $15 added to the account. So at the end of one quarter, balance $1,015. And then do it again. Let 3 more months pass, and we can calculate the balance after 2 quarters. So interest equals, well, the new balance is $1,015. We can multiply that by 0.06 and by 1/4, but basically what we're doing is multiplying the $1,015 by the periodic interest rate, 0.015, 1.5% quarterly interest rate, and we get hopefully a little more than $15 this time. $15.23. $15.23. A little rounding has to take place to make that happen, but we can do that. So $15.23. And so if we take the principal, now the new principal was what we had for the last 3 months, which was $1,015. And then we add the $15.23. Well, the 23 cents, why do we earn 23 cents more during the second quarter than we did during the first quarter? Right, the balance is different. The original $1,000 earned another $15, but the $15 interest that we earned during the first quarter earned the 23 cents or the 22.5 cents or whatever it was. So that's why it's a little bit different. Now, okay, how many quarters are there in 5 years? 20 quarters in 5 years. So we just have to do this 18 more times, and then we're there. We'd have the balance in the account after 5 years. All right, but this is algebra class, so there's got to be a better way than that. So let's see. Okay. Each time we're calculating the new balance, we're saying the principal plus the interest. Well, the interest is principal times rate times time. So it's the principal plus principal times rate times time. Now, again, this is algebra class, so we can factor out the P and say principal times 1 plus RT. So each time this is the calculation we're doing, we're taking the principal, the amount that was in the account for the last 3 months, and we multiply that by whatever 1 plus RT is. Well, what's RT? RT is the rate times the time. It's quarterly rate, so that's fixed. Time is fixed at a quarter. So actually the quarterly rate is 0.015. So RT is 0.015. That's the number we're multiplying at the end of each quarter. So what we should basically do is take P and multiply it by, well, not 0.015, but 1.015. If we leave the money alone for 3 months and multiply by 1.015, that will tell us the new balance. So we can do this faster. We can say, all right, take $1,000 and multiply by 1.015. Whoa, not that much. Okay, 1.015, and the balance after 1 quarter is $1,015. Well, let another 3 months go by and multiply by 1.015. And then the balance after 2 quarters will be $1,030.22.5. I'm thinking don't round. If the customer wants to withdraw the funds at this point, then round it. But otherwise, just keep it like it is and multiply by 1.015 a third time. So after 3 quarters, 9 months, it's $1,045.68 or so. And then to get the balance at the end of 1 year, if it were straight simple interest for 1 year, it would be $1,060, right? But it's a little more than that, $1,061.36, because the interest is earning interest, and so $1.36 more than what it would have been if it were just straight simple interest. Well, we'd still have to do this 16 more times if we wanted the total amount after 5 years. So there's got to be a faster way. How do we take $1,000 and multiply it by 1.015 20 times? How do we do that? Raise 1.015 to the 20th power. It's going to be 1,000 times 1.015 to the 20th power. And I left off the decimal. That is a fabulous sum of money. Let's try that again. If you take 1,000 and raise to the and multiply by 1.015 to the 20th power, it's $1,346.86. There we go. So that's the amount in the account, including the original 1,000, of course, if we compound quarterly. Now we've got a formula for that, so we don't have to sift through that each time. Compound interest formula. A equals P times 1 plus R over N to the NT. A is the amount in the account at the end of the time period. P is the original principal invested. R is the annual interest rate. We convert that to a decimal. And T is the number of years. We want to make sure that the interest rate, the units of time in the interest rate, and the units of time in the time are the same. If it's an annual interest rate, then T will be expressed in years. Sometimes, though, finance companies may work with a monthly interest rate, and in that case, the time should be expressed in months. So as long as those are consistent, this will work out for us. N, I like to call the compounding frequency. Compounding frequency is exactly as it says here. It's the number of times interest is compounded, or basically calculated and paid to the account every year. If it's quarterly, it's 4 times a year. If it's monthly, it's 12 times a year, so N equals 12. If it's annually, it's just once a year, so N equals 1. If we did that same problem using the compound interest formula, it would go something like this. Principal equals $1,000. Rate equals 0.06. Time equals 6 years. I guess that should be 0.066% per year. It's an annual interest rate. And N equals 4 because it is quarterly. Take the compound interest formula. Oh, can't see it there.
5 or 6 years.
Oh, is it 5 years? It is 5 years. Sorry about that. 5 years. So take the compound interest formula. A equals $1,000 times 1 plus 0.06 divided by 4 raised to the power of whatever 4 times 5 is. And just kind of notice what happens. When we take the interest rate and divide it by 4, that gives us the 0.05, the periodic, in this case quarterly, interest rate. And the 4 times 5, if we take the compounding frequency and multiply by the number of years, that's the total number of times interest is calculated and paid to the account throughout the process. So what we get is 1,000 times 1.015 to the 20th power. And that's the exact calculation we did before, just kind of building up to it using the simple interest formula. So should be the same final answer. What was it? 1346.86. 1346.86. Common mistake, I think, in evaluating this using the calculator. I'm trying to remember how it goes. What is the mistake? If you take 1,000 and multiply by 1 plus 0.06 divided by 4 and raise it to the power of, if you're using the TI-84 plus, it's not a big deal because you don't need parentheses up in the exponent. But if you're using the TI-83 plus, it is kind of a big deal. If you just want to write 4 times 5 there, rather than go into the trouble of actually multiplying 4 by 5 to come up with 20, if you don't put that in parentheses, it'll raise it to the 4th power, get an answer, and then multiply by 5. So be careful with the order of operations there. If you're using the TI-83 Plus, hopefully I got it there, and looks like I did. Let me see what's left in this. We do have a couple more minutes. So yeah, example 8, I reworked it. Find the amount that results from the given investment, different values. Let's look at example 10. I think we've got enough time to do example 10, at least maybe part A. Example 10, find the principal P, that is the present value. P stands for principal. It could also stand for present value if you wanted it to, that will generate the given future value. That is, if we're looking at our formula, A equals P times 1 plus R over N to the NT, and what we know is this, we have a goal. We want to have $10,000 in our savings account at the end of 10 years. If we could somehow find an account that pays 8% compounded annually for those 10 years, and we want to know how much should we part with immediately, right now. Just pretend like we don't have it. Set it aside, invest it right now, and let it grow so that it'll have a value of, or face value anyway, of $10,000 after 10 years. What you could do in this case, and I don't think it's a bad idea, is to divide both sides by the 1 plus R over N to the NT and actually solve the equation for P. Divide it by 1 plus R over N to the NT, 1 plus R over N to the NT, so that what you get is P equals A over 1 plus R over N to the NT, because what's unknown here is the present value. You've got your goal of A, which is $10,000. So P equals the goal, $10,000, the future value, divided by 1 plus 0.08 divided by, how many times a year are we compounding? If it's compounded annually? Just once. So N equals 1 to the power of whatever 1 times 10 is. So if I simplify it just a smidge, it'll be 10,000, 10,000 divided by 1.08 to the 10th power. Okay, so at an 8% interest rate, evidently the value is going to more than double in that 10-year time span. So if we'll just set aside $4,631.93 right now, maybe 94 cents just to be on the safe side, wait 10 years, come back, and I don't know what inflation will have done to the value of that $10,000 in 10 years, but at least the balance will be $10,000. So what we're looking to invest right now is $4,631.93. Again, maybe 94 cents just to be on the safe side since we're rounding here. E, and then see how it can be used to determine the limit, how high this number can go. So the number E is a vitally important number in applications involving exponential growth models, exponential decay models, and the compound interest is an example of an exponential growth model. Basically, when the assumption is the rate at which a quantity is increasing is proportional to the amount of the substance, whether it's money or whether it's the population of some species that's growing in an environment, if the rate of growth is proportional to the amount that's there at any given time, then it's exponential growth. That is, the bigger it is, the faster it grows. If that's the assumption that's made in determining the growth model, it's an example of exponential growth. And the number E is vital in that sort of study. The number E, one way of approximating the number E, is by considering the expression 1 plus 1 over n to the power of n for large values of n. Let's consider the value of the expression for a few small values of n. If n equals 1, it's 1 plus 1 over 1 to the power of 1. It's 2 to the 1, which is 2. If n equals 2, it's 1 plus 1 over 2 to the power of 2, which is 3 halves squared, which is 9 fourths, which is 2.25. If n is 3, it's 1 plus 1/3 to the third power, which is 4/3 to the third power, which is 64/27, which is 2.37, 0.37, so on. Well, it really doesn't get close to the number you'll find on the calculator. There are actually two different buttons on the calculator devoted to the number e, in whole or in part. The divided by button on the calculator, if you press the second button, followed by the divided by button, it'll display the number e, and you press enter, and you get a nice approximation for the number e. It gives the impression that it's a repeating decimal, what the calculator gives us. It looks like it's 2.718281828, and it would appear at first glance that it keeps doing that. It turns out that it doesn't. I forget if the next digit is 4, 5, or 6. It's something like that. But it turns out to be an irrational number. It doesn't terminate, it doesn't repeat, cannot be expressed as an integer divided by an integer. But there's another button on the calculator that's devoted to it. It's the LN button. We talk about logarithms today. If I can get through with the discussion of e pretty quickly, we'll talk about logarithms. If you press the second button, followed by the LN button right next to the 4, it gives e, and with the expectation it's going to be raised to a power. Since when e is used, it's almost always used in the context of an exponential function. So most of the time when you use the number e, you're going to be raising it to some power. So it goes ahead and says, all right, what power? How about the first power? If you raise e to the first power, well, that's what you get. You get e. So it's an irrational number. We're nowhere close to it yet. Let's try n equals 1,000. 1 plus 1 divided by 1,000 is 1.001 to the power of 1,000. And the calculator says that's approximately equal to 2.7169. Now that agrees with the actual number e, with the 2 and the 7 and the 1, but that's about it. Let's try n equals 1 million. That would be 1 plus 1 divided by 1 million to the power of 1 million. That's going to be 1.00000. Is that a millionth? Tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths, raised to the power of a million. So I need five zeros in between the ones there. So 1.12345, and then a 1 to the power of 1, 1, 2, 3, 4, 5, 6. A little bit closer, we get more decimal places of agreement with the number e, 2.71828. So about 6 significant digits where it agrees, and it would actually round, I guess, to 0 there. So we only get the 6 significant figures of agreement. So 2.71828. I think if you put in 10 billion, you can get it to agree to as many decimal places as the calculator is willing to show. But the key here is the expression 1 plus 1 over n to the n is the expression that we need to come up with the PERT formula. A equals P times E to the RT. I call it the PERT formula. It's just kind of P times E to the RT. A good mnemonic device there for helping you to remember that. If you compare that to the formula for finitely compounded interest, 1 plus r over n to the nt, what it actually does, and it'd take me about 5 to 10 extra minutes to go through the details, what it actually does is it takes the formula for compound interest a finite number of times, and it asks the question and then answers the question, what happens as n approaches infinity? If we look at the way the number e is defined, it's what happens when the expression 1 plus 1 over n to the n approaches as n approaches infinity, and it takes just a little bit of work to show the details, but as n approaches infinity, this expression actually approaches, let's see, p times, I want to say 1 plus, well, I guess I should say this expression approaches the value of this expression. I'm leaving out some key details there, but not like they're going to be on the test. In a pre-calculus or calculus class, I'd be a little bit more careful about showing the connection there. But if we want to know what's the maximum amount $10,000 can grow to, when invested for 10 years at 8% annual interest rate, we would say A equals $10,000 times E to the 0.08 times 10. It's actually a simpler calculation than the finite compound interest formula. $10,000 times second button ln, and then up in the exponent, again, TI 83 plus users, unless you just look at the 0.08 multiplied by 10 and calculate 0.8 directly. If you're having the calculator do the 0.08 times 10 for you, be sure to enclose it in parentheses. Enter. So that is it. How much more is this than compounding? It's gone. How much more is this than compounding hourly? Or, yeah, we did not do minutely. Hourly. Well, we say it's $22,255.41 when it is compounded continuously. It's pushing the envelope to its limit, compounding secondly, millisecondly, nanosecondly. What's the maximum amount? This is the maximum amount, and it's how much more? Whoa, a good 8 cents more. Yeah? Yeah. A good 8 cents more on a $10,000 investment on over 10 years at 8% annual interest rate, compounding continuously than compounding hourly, for example. So, in problems that say compounded hourly or annually or quarterly or monthly, it's going to be this. That's the formula that you want to use. If it says compounded continuously, that's the only case where you use the PERT formula. A equals P times E to the RT. Yes, sir?
And that's to only find its maximum limit?
Right. The maximum amount that $10,000 can grow to in that time span at that interest rate. It's like N equals infinity. Or it's like taking the limit. It is taking the limit as N approaches infinity.
E is that defined number, like I would be defined, E will always be that number?
Yeah, E is always going to be that number, 2.718281828, and on and on and on. Yeah, I believe the next digit is a 4. If it weren't a 4, we'd probably round that to a 9. But I think it's if we're 5 or greater, we'd round it to a 9. Next one, I believe, is a 4.